What are the features of brains that are essential to convince us that we have truly a neuromorphic system? The question is, why do we do neuromorphic at all? It depends on what you want from it, really. Do you want faster computers? Do you want better artificial intelligence? What is it that we want with neuromorphic computing? We want neuromorphic primarily because we're the best examples we have of great intelligence, great biological intelligence. Well, some people might regard that as a very particular case that comes with so many details that we can definitely abstract it all away and transform it into matrix vector multiplications of various sorts. But it does feel like the brain still has stories and still has lessons to teach us, doesn't it? Though this does run into the so-called problem of induction. Just because all examples we know of biological intelligence are like this doesn't mean that all examples of intelligence will be like this. In addition to being a computational neuroscientist, I'm also a cognitive scientist. And as you may know, cognition is often referred to as the capacity of brains to make sense of stuff that happens. When I think about intelligence, I depart from the type of intelligence that we observe, the one that was discovered by evolution, and it is as impressive as it is limited. The thing about our particular type of intelligence is that it seems to live in a sort of cognitive Goldilocks zone. Cosmologists talk about the Goldilocks zone as the cozy spot that planets like the Earth have to find before they have the subset of chemistry most conducive to life. Water for diffusion, daily energy intake. Even if we can imagine life in other circumstances, there are cogent physical arguments for how this peculiar point in parameter space is such a lovely spot for life. And when applied to our type of intelligence, this Goldilocks zone refers mostly to how our world seems to be sufficiently described by Newtonian mechanics. Our cognitive system makes sense of time, space, mass, gravity. Even if modern physics tells us that all units can be subsumed into some combination of Planck units, our cognitive Goldilocks zone, the units we use are units of cognitive meaning. To make this more concrete, this is to say that real cognition is not scale invariant. We operate in a very particular slice of physics. Things fall in meters per second. We understand speech in 1 times its speed, maximum beyond that. Our narrow sensory channels are no longer able to parse the information contained in physical signals. Even if we can squeeze 2 hour YouTube in 1 second or 1 minute without loss of information, all of this information would be lost on us. And action is not time invariant either, neither is color or the sound we perceive. So by extension, the computations that brain produce happen within a very narrow range. We humans can look at ourselves, at our intelligence, and imagine scale-invariant computations. So in silico computers, in von Neumann architectures, in Turing machines. This is because we managed to abstract many of the principles of biological computation into computer science or computer engineering. We can write down recipes and follow them through, leading to the paradox of algorithmic complexity, Gödel, Turing, and Chaitin. When I stare at the ceiling, I believe that our intelligence is a subset of Turing computation, not a superset. Although the universe might be a Turing computer, is the algorithms that matter. So the axioms of computer science are lifted from life the same way as numbers are lifted from objects, distances, and weights. Our brains approximate universal Turing machines because we can follow instructions in a sequence and keep record. Turing idealized the kind of instruction based on computations our brains can follow, and it stretched our memory space to infinity and reduced our operations to strictly sequential operations. We can kind of act as universal computers, and in the entire animal kingdom, this ability has emerged in full glory only in us humans. Now, the thing about universal Turing computing is that by idealizing computation, it can get rid of most of the physical constraints, but this truly matters, I think, if we're building a biological intelligence or a brain. I'll argue that the consequences of the abstractions make explanations of mental computations based on Turing flawed. If we want to confer to an intelligent system the types of properties that we observe in ourselves, we should primarily be searching for ways in which biology gives rise to interesting boundary conditions and potentially to specific types of emergent information. And we've been comparing brains and computers for a while now. John von Neumann himself diligently wrote this book, Apples and Oranges, though now we have to expand that to also include the emulation of intelligence via neural networks. And I came up here with a little table. I'm not going to spend time in this slide because each of these is a philosophical can of worms. Nevertheless, these comparisons can help us spot what is potentially missing. In any case, from the table before, I conclude that artificial neural networks make things more interesting, seemingly more biological. With nonlinearities come interesting dynamical systems, perceptrons, feed-forward neural networks, categorization. We can explain spikes and a few other population phenomena. Nevertheless, after a period of neural network bonanza, I'd argue we're a bit stuck with respect to the level of representation in our neuro AI models. Particularly after realizing that spikes are primary information bearers, we kind of got stuck at this level of analysis. That's not exactly surprising because we have had great successes in understanding spiking and population encoding. We have solid grasp of spike encoding and transfer functions via models such as the HH model and the IF model. We have great collection of different ANN types and what they excel at. We have solid understanding of the best ways to backpropagate in networks of ReLUs and which correlations to calculate. The Nobel Prize was awarded for these great neuro AI metaphors and achievements. Much of this has started with the Hodgkin and Huxley model. Now, on the basis of spikes and sigmoids, we came up with great analogies to reproduce and reconstitute function. We ditched complexity from complex arbors, such as those of the Purkinje neuron of the cerebellum, and translated everything to weight vectors and connectivity matrices. Still a question, though. These metaphors, where do they bottom out? We can abstract a substantial part of neuronal complexity away, and we land with things we can actually mostly understand and are really, really useful. We can build lovely pattern recognition machines that do not suffer from the XOR problem. Since 1977, we've been building deep networks that can categorize written digits. We have a lovely vocabulary of structure-function relationships, like sort of engineering of the brain, if you like. And for a while, and even now, many are convinced that this is the ultimate level of analysis. With artificial neural networks, we became unreasonably competent at doing things with patterns. We backpropagated the hell out of data and tuned connectivity matrices to extremes, making best use of data correlations and of gradient descent. But there's a cautionary tale. As a friend of mine says, if all you have is a hammer, treat anything like a nail. And I don't think that scientists want to treat everything like a nail. I think we want more than a hammer. And while the types of neural network architecture is clearly part of the picture, there are substantial features of biological intelligence currently missing. Everything is a pattern, and so everything works. We're able to kind of create great jobs of neuroengineering and spike-based systems that perform complex cognitive functions. The unreasonable effectiveness of neural networks has kind of created a blind spot to actual neurobiology and their solutions. I definitely don't blame anyone. This is a lovely hammer. We all use it. We all love it. It's rather straightforward to implement in hardware. Problems is loads of interesting stuff from biology seems to be missing, doesn't it? Some of the stuff we've implemented. So we have lovely neuromorphic spiking since 1991 in this paper here, A Silicon Neuron by Rodney Douglas. The moment that we started writing these metaphors as circuits, then we basically knew what was the analog information bearer. And we can reproduce a wide variety of real spiking patterns. We have great theories like the Zhikevich model that is also computationally efficient. And we've implemented a number of different off-the-shelf systems that can do this stuff. So Loihi, True North, brain scales, and different, like all of them looking at the problem slightly differently, but many of them getting the one thing equal, which is adaptive exponential integrated fire. In fact, integrated fires most likely. And the non-linearities land only in the production of the voltage traces, the output voltage traces in many of these cases. So we look at neuromorphic as the implementation of these equations, really. And we do think that that matters too. Personally, I mean, we have been trying to implement memristors to model ion channels that work at the cognitive Goldilocks zone for neurons. We are able to emulate, using novel materials, the potassium channel dynamics and the right, in the appropriate time scales of the neuron, right? So like real time, but real time. It works great in the simulation, and we are pretty happy with this. But there's just so much biology we don't want to ditch, isn't there? I mean, and particularly the kinds of cool solutions that biology has. For the biological intelligence that evolution came up with, which seems to reproduce intelligent behavior, is often at odds with how artificial neural networks in more than a few ways. Everybody knows this. Machine learning networks need too many examples, too many training epochs. They are not robust to failure. Their ability to learn on the fly is only there if it's been somehow pre-encoded. ANNs are in general not very dynamic, with some notable exceptions, but even those. And recursion and self-connections are things often to be curbed. As you see in transformers, we simply unfold time and treat it as any other pattern, and then add context by creating attention mechanisms that connect through layers. But the living brain is computing in the now in a way that is only distantly related to having state influencing context via skipping layers. The problem with using biology is that biology does not seem to bottom out very well. It turtles all the way down. Every phenomenon is a bit of a rabbit hole. Modeling of the type we do in computational neuroscience ranges from simple to complex depending on what is the phenomenon under the microscope. Sometimes a neuron looks like a harmonic oscillator, sometimes it looks like a source of infinite complexity. Nevertheless, progress in modeling seems to be related with the discovery of particular abstractions, intense reductions of dimensionality from the original biological problem. But by trying to fit mathematical clothes to biology, the fit's imperfect. The cloth may be too tight in some places and hang loose on others. Now, to orient us in the selection of relevant biological mechanisms, we have scales to help us, and the known biological consequences for certain biological mechanisms. For instance, if the level of analysis is our focus is encoding information via spikes, we do not need to include a lot of the other bioelectrical and biochemical phenomena that we observe in the brain. Moreover, it's crazy. Which rabbit hole should we pursue? All of these biological mechanisms are crazy detailed, like synapses. There's so many different mechanisms inside. So the big question is, what matters of matter most? And if this is the map, like I've created a map here, where must we go next? I mean, what are the things that we need to implement? And why? So we can implement loads of things. We can have multimodal plasticity, the idea that you can have multiple types of concurrent layers of learning, not only simply activity dependent on one dimension. Activity-dependent plasticity actually happens everywhere, so how do we represent that? Is that useful? Homeostasis is something that neurons want and brains require, but neural networks do not usually put much effort or attention to. We talk about dynamical transitions like synchronous to asynchronous transitions, oscillations. Important also the fact that we have heterogeneous neurons. There are some phenomena that we still have to explain before we can actually implement them in neuromorphic computing, such as representational drift. I'm going to get into this just a bit so that you have a sense of where do I think that the opportunities lie for neuromorphic computing. I'm going to skip this. So representational drift is the idea that even if you record a neuronal population while you're doing some gesture, for instance, say you're drawing a big circle on a whiteboard, and you do this today, tomorrow, and the day after tomorrow, the pattern varies over time. Why? How? I mean, so we don't know that. In artificial neural networks, the connectivity after training does not vary. And they seem to, what we do, it varies day by day in a smooth way. It's a smooth manifold in this enormous parameter space. And we've been trying to study this by making super high-dimensional models of the inferior olive and the cerebellum to try to understand how their dynamics relate to these types of representational drifts and homeostasis. Ultimately, we're talking about trying to discover which is the true neuromorphic that compels as the future steps for neuromorphic. And there is a tension in the future steps of neuromorphic. On the one side, like if you're going to invest engineering energy into something, you want general mechanisms, you want sort of like simple mathematics and general principles you can abstract away and put in hardware. And you want clear consequences. You want to know why you're doing it. You want static parameters. You want your machine to sort of like do the same thing every time. And you'd rather basically pick up a min-raster plan and copy it like hundreds of millions of times, and then we're done. But computational neuroscience offers us very specific mechanisms, complex dynamics, multiple causal chains, dynamic parameters. We're all changing all the time, and uniqueness of individual neurons. So how do we go from here? Where do we go from here? And I think that there are a few things that I would call non-negotiables, things that we definitely really have to commit to if we're going to see the emergence of the next stage of neuromorphic computing, which are the so-called non-negotiables. For instance, I think gonna have to have activity-dependent plasticity more or less everywhere. It must adapt with use, preferably in multiple scales. Without continuous rewiring is static electronics. Also, population-based coding with representational drift, so there's an invariance function despite shifting representations. These are things that we have to be able to contain in our neuromorphic systems. And a few of the older stuff that we still really need to pay close attention to would be things like delays and the abilities that they might confer to these systems. In the distant future, we might have big brains, and the brains will have, metaplasticity, multimodal learning rules, loads of criticality, nonlinear dynamic integration. All of this stuff preferably will be there in a positronic brain. But for the moment, I would say that we can concentrate on ideas of constant plasticity to try to understand how to create brains that are really robust, more robust than anything we had seen ever before. And this is what I had for you today. I hope that this was understandable and that it made sense, because we are cognitive organisms in a Goldilocks zone, and we love to make sense to each other. I'll take questions in the YouTube comment section below.